In this lecture, we are going to cover introductory concepts of vectors, vector addition, subtraction, relative velocity in two dimensions, vector resolution, river boat problem, dot and cross product of vectors with their physical interpretation. To begin with, vectors are defined as the physical quantities having both magnitude and direction, and these physical quantities must obey vector algebra. If any physical quantity only possesses magnitude, then it is termed as a scalar quantity. Having both magnitude and direction doesn't make sure that the quantity will be a vector. As per the definition, the physical quantity must obey vector algebra. For example, current has magnitude and it always flows from higher potential to lower potential. So, direction too can be associated with current, but it does not obey vector algebra. Hence, it cannot be considered as a vector. Example of vectors are displacement, acceleration, velocity, force, linear momentum, etc. And some examples of scalar quantities are length, mass, distance, speed, etc. How do you represent a vector? Graphically, a vector is represented with a straight line with an arrowhead. The starting point is termed as the tail and the ending point is termed as head of the vector. The length of the straight line is called the magnitude of the vector and the arrowhead shows its direction. We need to remember that magnitude of a vector is always a scalar quantity. In writing, a vector is represented with a single letter with an arrow on it, or it is represented in a bold-faced letter. Its magnitude is represented by the same letter but without using the arrowhead. The magnitude of a vector is also represented by the modulus symbol explicitly with the vector. We need to remember the magnitude or modulus of a vector is always a scalar quantity. Vectors can be added, subtracted, multiplied. We will see that vector multiplication can be of two types. When the multiplication of two vectors resulted in a scalar quantity, then we term it as a dot product. And if the multiplication of two vectors resulted in a vector quantity, then we term it as a cross product. However, division of a vector with another vector is not a valid operation in vector algebra because the division of a vector by a direction is not possible. Now, let us see some important terms used in vector and what these terms mean. Equal vectors. When two or more vectors are equal in magnitude and direction, then these are called equal vectors. Unequal vectors. If either magnitude or direction of two vectors is not the same, then these are called unequal vectors. Parallel vectors. If two vectors act in same direction, then these are termed as parallel vectors. Parallel vectors may or may not have equal magnitude. Hence, equal vectors are always parallel, but parallel vectors may or may not be equal. Antiparallel vectors. If two vectors act in opposite direction, then these are termed as antiparallel vectors. Again, their magnitude may or may not be the same. Negative vectors. In vector algebra, negative means opposite in direction. The negative of a vector means a vector having the same magnitude but in the opposite direction. Collinear vectors. Vectors acting along the same line or in parallel lines are called collinear vectors. Coinitial vectors. Two vectors are said to be coinitial when their initial point is the same. Null vectors. In vector algebra, we will see when two vectors are added or subtracted, the result we get must also be a vector. So, if we add one vector with its negative vector, we should get a zero vector. These vectors are having no magnitude and they can be arbitrarily directed. These vectors are defined as a null vector. Unit vectors. A vector having unit magnitude in any particular direction is called a unit vector. In vector algebra, we will see the importance of finding the angle between two vectors. When two vectors are placed with their tail at the same point, then the angle between them, which is less than or equal to 180 degree, is called the angle between the two vectors. So, parallel vectors are having zero angles between them and antiparallel vectors are having 180 degree between them. Multiplication of a vector with a scalar quantity or a number is a valid operation. The process increases the magnitude of the vector without changing the direction. Here in the first example, the magnitude of the vector increases by 3 times in the same direction. In the second example, vector is multiplied with a negative number, hence its magnitude first increased and then because of the negative sign the direction got reversed. We can see this principle applying in various cases like finding linear momentum, which is the multiplication of a velocity vector with the mass of an object. The first operation in vector algebra is vector addition. A vector addition can be performed using mainly two laws. The first one is the triangle law of vector addition. Here, two vectors are acting on a point with a certain angle between them. Triangle law states that if two vectors are represented in magnitude and direction by the two sides of a triangle taken in the same order, then the closing side of the triangle taken in the opposite order represents the resultant in magnitude and direction. In this process, as the tail of the second vector is placed on the head of the first vector to obtain the resultant, hence this process is also named as head-tail method. Quantitatively, we need to obtain the expression of magnitude and direction of the resultant vector. Here, some geometrical steps are shown to calculate the magnitude of the resultant vector, and the angle alpha can also be calculated between the resultant vector and the vector A to specify the direction of the resultant vector. Magnitude of the resultant vector is r equal to square root of a square plus b square plus 2ab cos theta, and the angle alpha is alpha equal to tan inverse b sin theta by a plus b cos theta. Using parallelogram law, we can also perform vector addition. Parallelogram law states that if two vectors acting simultaneously at a point are represented in magnitude and direction by the two adjacent sides of a parallelogram, then the diagonal of the parallelogram passing through the point represents the resultant in magnitude and direction. If we compare the schematic for the calculation of the resultant vector using triangle law and parallelogram law, we can see the figures are very similar. The calculations to evaluate the magnitude and the direction of the resultant vector are also similar. Based on the angle between the two vectors, the resultant vector changes. If theta is 0, r is equal to a plus b and alpha is 0. If theta is 90 degree, r is equal to square root of a square plus b square and alpha is tan inverse b by a. If theta is 180 degree, r is equal to a minus b or b minus a, and alpha is 0 or 180 degree based on the magnitudes of a and b. The addition of multiple vectors can be performed using a polygon law. This law can be considered as an extension of triangle law. Polygon law of vector addition states that if a number of vectors can be represented in magnitude and direction by the sides of a polygon taken in the same order, then their resultant is represented in magnitude and direction by the closing side of the polygon taken in the opposite order. To show that this law can be explained using the triangle law, we can break the polygon into number of triangles. From the figure, we can find that the resultant of A and B is R1. Then the resultant of R1 and C is R2. Then the resultant of R2 and D is R3. And finally, the resultant of R3 and E will give the resultant of all the vectors R. The vector addition follows commutative law. It means A plus B is equal to B plus A. Again, the vector addition follows associative law. This means A plus B when added with C becomes the same when A is added with the resultant of B plus C. The second operation in vector algebra is subtraction. Actually, in this case we add two vectors, but before performing the operation, the direction is reversed for the vector which needs to be subtracted. The rest of the operation can be performed either by triangle or parallelogram law. At next, we have relative velocity. Suppose two objects A and B are moving with velocity VA and VB respectively. Now velocity of A with respect to B can be evaluated as VAB equal to VA minus VB. Similarly, the velocity of B with respect to A can be calculated as VBA equal to VB minus VA. Now let us apply the concepts of relative velocity in solving rainfall problems. Rain is falling vertically downwards with a velocity Vr and the person is moving towards the east with velocity Vm. To the person, the relative velocity of rain will be in the direction of Vrm. Vrm can be calculated by reversing the direction of Vm and then adding it with Vr. That is, to the person, the rain will appear from the direction of the resultant vector Vr minus Vm. Vector resolution is also a very important topic. When we add two vectors, we replace the separate vectors by a single equivalent resultant vector. We can also perform the reverse operation, that is, we can replace a single vector into any two vectors whose sum gives us back the original vector. This process is called the resolution of a vector. Vector resolution along mutually perpendicular axes often simplifies the complexity of many practical problems. When a vector in a plane is resolved into two components at right angles to each other, the component vectors are called rectangular components of the vector. In the illustration, vector A is making an angle theta along x-axis. We can easily resolve the vector along x-axis and y-axis, which are mutually perpendicular to each other. The component of vector A along x-axis is a cos theta and along y-axis is a sin theta. Next, we are going to discuss the river boat problem. In this kind of problem, generally we have to find either the minimum time required to cross the river or the minimum distance covered by the boat to cross the river. Suppose the boat is capable of moving with velocity Vb in still water. Water is flowing from left to right with a velocity Vr. If the width of the river is W and the boat is launched with an angle theta from the vertical path, then in general the time required to cross the river will be W divided by Vb cos theta. Time taken becomes minimum if cos theta becomes 1, which means theta value must become 0. Therefore, the boat must be launched directly towards the opposite bank of the river. By doing so, the boat will get drifted downstreams by a distance Vr by Vb into W. To cross the river in the shortest path, the boat should move in such a direction that the horizontal component of its velocity is neutralized by the velocity of the river, which means Vr must be equal to Vb sin theta. From this equation, we can calculate the value of theta to be sin inverse Vr by Vb. Vector multiplication is of two types. The first one is dot product or scalar product. In this multiplication, we multiply two vectors to get a scalar quantity. One such example is work done. We know work done is a scalar quantity and it is the product of force and displacement. Both force and displacement are vector quantities. If there are two vectors A and B making an angle theta, then the dot product between them is defined as AB cos theta. From the concept of dot product, we can calculate the angle between the two vectors. Theta will be cos inverse A dot B divided by AB. If the vectors are resolved into three mutually perpendicular components as A vector equal to AX I cap, AY j cap and AZ k cap and B vector equal to BX I cap, BY j cap, BZ k cap, then the dot product of the two vectors is A dot B equal to AX bx plus AY by plus AZ bz. Dot products obeys commutative and distributive laws. Another type of vector multiplication is the cross product or vector product. In this multiplication, we multiply two vectors and we get another vector as the product. One such example is the torque, which is the vector product of displacement vector and force. If there are two vectors A and B making an angle theta, then the cross product between them is defined as AB sin theta n cap. Physically, the magnitude of the cross product is equal to the area of the parallelogram formed by the individual vectors. N cap shows the direction of the cross product and can be determined using the right hand thumb rule. If we curl fingers of the right hand from the first vector to the second one through the small angle, then the direction of the thumb will point the direction of the cross product. This is why the direction of A cross B is pointing upwards and B cross A is pointing downwards. Cross product do not follow commutative law but follows distributive law. The cross product of any two vectors resolved into three mutually perpendicular components is expressed in the following determinant form. To sum up, in this chapter we have discussed the introductory concepts of vector, vector algebra, river boat problem, vector resolution, etc.